Hey there, how's everyone doing? Hopefully you're having an amazing day. I am. And today we're going to talk about searching and indexing across a singly linked list. Here's the actual code. As usual, I know people just want to jump in here, get the code, copy paste, and explore on their own. That's fine. You can also check the GitHub. It's in there. Basically, we're going to do two separate functions. We're going to be doing a search function, which is just going to be given a specific item, such as a number that we're going to search for. We're going to check if that's in the list, and we're going to return true or false. The next one we're going to do essentially follows the same logic. However, instead of returning true or false, we're going to return a specific index. So we're still going to take a function that takes a specific item, such as a number to search for, and we're either going to return -1 if it's not found, or we're going to return the index at which that node is found, at which whatever node containing that item is found. So that's what we're going to do here. Here's the actual code if you just want to get started now. Otherwise, you can stick around and I'll talk about it. Here is the sources as usual. Nothing's really changed there. Let's check out Visual Go here to kind of look at how searching works. Alright, so I have in Visual Go here, I just have these, I just have the list here. I got 1, 2, 3, 4, 5, 6, 7 nodes in this list, a head pointing at 22 and a tail pointing at 89. And just remember, in my implementation, I'm not implementing the tail yet. I will at the end. But it's optional, and I just want to show people how you don't have to use it first, and then I'll show you how to use it. All right, so let's search. Let's search for 5, which does not exist in this list. So what are we going to do? It's a pretty simple concept. We're going to start at the head, and we're going to check, does our search key exist at that node? Okay, it did not, so all we do is we go on to the next node. And we do the same thing. Is 5 exist at that node? No, 2 does. Okay, let's go on to the next node. No, we have 77, that's not equal to 5. Go to the next node. 6 is not equal to 5. 43 is not equal to 5. 76 is not equal to 5. 89 is not equal to 5. Now we've reached the end of the list, or we're basically our next pointer. So this node, if you were to imagine that this last node here, if it had a next pointer, it basically points to nothing. It's none. So the second we realize that this next pointer points to none, we know we're at the end of our list. If we haven't found it, our search key by then, we just return false. Otherwise, if we search for something that is in the list, I mean, it's pretty simple concept. Let's search for something that is in the list. 76 right there. Let's try it again. 76 right here. And let's see what this does. Starts at the head, checks node by node. And then boom, it finds it, and it's going to eventually return either true or false based on if you're using the search, or if you're using the index method, it's going to return the actual number which it was found at, which in this case is 5, because you're still using zero-based indexing. All right, so this is still index 0, this is index 1, index 2, index 3, index 4, index 5, and we found it at index 5. Okay, so searching is just going to return true or false. Index is going to return the actual integer index in which it's found at. Here's the code for the search broken down again. It's O to the n time complexity. Basically, yeah, you start at the start of the list there and search iteratively. You traverse the entire list, checking the data of every node. If what you find there is if you don't find the item, then obviously you return false. If you do find the item, then you just return true. Okay. The next one, index, essentially the same logic. It's still O to the n time complexity. This time we're just keeping track of a index variable. Other than that, it's basically the same. You don't need to use a search versus an index. There's nothing that says you have to have a search function and a index function. You very well could just have a single search function or just combine the two. Basically just have something that if you check if something's in a list, you're either going to get an integer value back, and if you get -1 back, you know it's not in the list. So you can really use the index for your search as well. I just wanted to show you the two different implementations based on what you're trying to do. All right, I'll go ahead and jump into my code editor here. All right, so I'm in my singly linked list class. I already wrote some test cases here for the search function. So basically, here's all my test cases. I'm first going to create an empty list, make sure that the head is none. Then I'm going to go ahead and I'm going to search across an empty list. So for this one, my list should be empty. So I want to make sure it doesn't fail if I have an empty list. And then I'm going to add some elements, and for each one of those, I'm just going to go ahead and search, making sure all those elements exist for after each add. This way, I'm checking, making sure the search works if it's one element. If it's multiple elements, it's also going to make sure that it works if it's not at the head, so on and so forth. And then I'm just going to throw some random numbers at it, numbers, negative integers, floats. Just make sure that it can handle things that aren't in the list and some data types that we're not really expecting, negative integers and floats. So I've already got the test here for the search. I can run it and it's going to give me an error. Okay, singly linked list object has no attribute search because I haven't even wrote the function yet, so that's perfect. But test-driven development, write our test cases, make them fail, and then we'll fix them. So let's go in here and let's add it. The first thing I'm going to do is come up here to my module docstring, and I'm just going to say, hey, I'm adding this function, which is what? It's a search. It's going to take an item. I know it's going to be O to the 1, and it's going to search for the item in the list. Just optional. You don't have to keep track of your documentation if you don't want to. All right, so let's write it. So def search, it's going to take self as the first positional parameter as always for any instance method, and it's going to take the item or kind of the search key we're looking for. I'll keep track of I'll do my documentation later. I don't want to waste time on documentation. Item is going to be basically any data type here, and this is going to return a Boolean. Okay, so what are we going to do? Well, we know we need to start at the head of the list. So let's go ahead and create a pointer, or just a variable that's going to keep track of whatever node we're currently looking at. So we're going to say the current node, and what's it going to start at? It's going to start by default at the head. Basically, all we're doing here is we're creating this variable, and it's going to point to right here. It's going to point to the head. And then we're going to go and we're going to check its data there. And if we don't find it, we're going to move it to the next spot where it's going to point to 28. And we're going to check that. And if it doesn't exist there, we're going to move it to the next spot, which is 14. So on and so forth until we reach the end of the list, at which point our node, whatever our pointer is pointing to, is going to equal none because there's nothing there. That's when we know we're at the end of the list. So this is how you do it. Current node is self.head. We already kind of talked about that. Now we just need to go ahead and iterate over our list. Well, we're going to use a while loop because we don't know exactly when this is going to end. But let's go ahead. We're going to use a while loop. And what's our exit condition? Well, we're going to exit if the current node is none. All right. All right, because that means I got to the end of the list. The current node is none. And then also I want to check as well if the current node dot get data. So the data that exists inside of the node that I'm currently at is not equal to item. As long as both of these conditions are true, it's not none. And then it needs to be is not none. There you go. Well, the current node is not none, and whatever is inside of it is not what I'm looking for. I'm going to continue searching. So all I have to do for that is say, hey, jump to the next node. So current node is going to equal to current node.getNext. Then finally, I know this is either going to exit if the current node is none, which means I'm at the end of the list, or I'm going to have it's going to point to a specific node in which it found an item. So since this is going to return a Boolean, all I have to do is say return current node is not none. Because if it is none, this is going to return false, which means I'm at the end of my list and I didn't find the search key. Otherwise, if current node is not none, that means it found the get data actually found something, right? And it's pointing to a specific node. So current node is going to be a node pointer, a node object, and this is going to return true because it's not none. All right, let's go ahead and let's run our tests. Okay, all my tests work, so that's great. Let's check it in the terminal. Yep. From singly linked list. Import singly linked list. Boom. Let's create a list object. Singly linked list. Let's add some stuff to it. ll.add10, and we can print it every time we add just to make sure. So this is what my list is. I got 23 as my head, 17 as the next node, and then 10 is the last node in the list. So if I do ll.search for 23, I should find it. ll.search for what, 17? That's perfect. ll.search for 10. And if I do ll.search for negative something, it's false. ll.search, we can search for a string. ll.search, we can throw a dictionary in there probably, because the data type we're searching for really doesn't matter. And let's do one more check here again. ll. is going to equal a new singly linked list. We're just going to empty it. And we always want to search or check our functions against empty test cases too. So let's just say ll.search for -19. Making sure again that this works with a empty list. And it does. So that's the search. The index is going to be essentially the same. So I could copy this. Actually, I'm not going to copy it. I'm just going to go ahead and write it out. I also have some test cases already built for my index function. So I'm going to uncomment those. And it's the same kind of concept. We're basically going to create an empty list first. Then I'm going to search across an empty list, because you always want to test your algorithms against an empty list as well. You'd be surprised. You could write a whole algorithm, it works great, and then it fails against an empty list. So we're saying on an empty list, if I search or call the index function, pushing in some random search key, it's going to be -1. That's what I'm going to have my function return. You could return 0, or you could return whatever you want here. -1 to me tells me it's not in the list. Otherwise, ll.add, we're going to add 17. 17, since it's the first element we added, should be at index 0. So I'm going to check that. Then I'm going to add 23. Now remember, 23 is being added to the beginning of the list. So 23 right here is going to exist at index 0. 17 now has been moved to index 1. And then when we add 49, 49 goes to index 0. 23 is index 1 now. 17 is index 2. And then I just search for some random stuff across the list 2 that I know is not in there, and I expect it to return -1. So those are my test cases. I can run it now. I know it's going to fail because I haven't implemented the method at all. What am I doing? Test.py. Is it tests? Yep, okay. Okay, singly link object has no attribute index. So let's go ahead and do that. So def index, self, and item. All right, the first thing I want to do is I just want to fail fast. So basically all that means is I want to handle that case in which my list is going to be empty. So it's easier to do it here if I just do if self.head is none, right away return -1. So this is actually going to pass this first test case right here. Okay. If I don't do it here, I'll just do this and we'll just say, hey, it returns none. or I do a pass statement, which will return none by default. Okay, I fail. Assert equal ll.index19 is not equal to -1. It returns none. The function returns none because I have no return statement. So by default in Python, it returns none. And that's this test case here. We're searching for 99 on an empty list. I expect to get -1 back. So let's fail fast. If the head is none, let's just straight up return -1. Now this test case is going to pass. Okay. The next test case fails, which is this one right here. ll.add, we're going to push 17 or add 17 to our list, and then we're going to say, hey, it should be at index 0, and I'm getting none. The reason I'm getting none here from my function is because if self.head is none, we're going to return -1. However, now we've actually added something to the list. So this conditional here is not going to evaluate to true, so we're not even going to try this, and we're going to come down here, which doesn't return anything. So all we need to do down here is handle the almost exactly what we did up here for the searching, almost. We're going to say a current node is going to equal to self.head, because I know the head points to a node object. I'm going to create a variable that is going to be used to track what index I'm at, index 0. And, well, yeah, we're going to start at index 0. Then we're going to use a while loop again, and we're going to simply say, hey, while current node dot get data is not equal to item. So slightly different than up here for my while condition. This one right here, I'm just going to say, hey, whatever node you're at, check that, and check the item. Okay, so if the current node's get data is not equal to what we're looking for, what do we want to do? Well, we know we didn't find that value at that given node. So the first thing I want to do is go to the next node. Current node is equal to current node.getNext. I also want to increment this index because I just moved a node, so I need to keep track of how many nodes I visited. So I'm going to say index is equal to, I'll just do a plus equals 1, which will increment it. Then I need to do a final check to handle the case. Just 1 second, let me bring up a browser. I need to do one more check to handle the case where my current node is pointing to back here, where it's none. Okay, because let's say I was just at the end, I was at the tail of the list, I checked it, okay, 89 is not what I'm searching for. I'm still going to increment my index. I'm still going to increment my, or move to the next node. So I need to handle checking if we're at the end of the list and my current node now evaluates to none. So all we're going to do here is throw a little if statement inside of this while loop. So if current node is none, we've reached the end of the list. What are we going to do? What do we want to return when we reach the end of the list? -1. And then finally, if I get all the way down here and I break out of this while loop, because this while loop is going to exit the second it sees an item that matches the data. Okay, so whenever it sees a node with the given data that is what I'm searching for, this while loop is going to exit, and the index should be pointing to the node that I want, so I can just return the index. And proof is in the pudding, so let's go ahead and test this. Yeah, let's just test it right there, and then I'll make it smaller. There we go. So all my tests worked. So let's look at this in the terminal here. Here's my function for the index. Let me open up Python and import the class. Create a list object. Let's first search for something, so index -99, -1, so that's what's happening there because the head is none, right? So ll.head is none. Well, it's gonna not print anything. There we go. So then when I do index of 99, none of this code at all is evaluated because the head is none, so it's gonna return -1 by default. But now if we add something, ll.add, let's add 17. I can print my ll And I got one item in there. So now if I say ll.index and I'm looking for 17, it's going to find it at index 0 is what I expect. Okay. And just to check, I should still get -1 for that value that doesn't exist, the -99. Okay. And I can keep pushing things all day. 23. If I print my list and I do index on 23, it should be at 0. ll.index of 17 should be at 1. ll.add another one, 92. Print ll.index of 92 is going to be 0. Index of 23 is going to be 1. Index of 17 is going to be 2. Index of 17. But all right, that is the search and the index function. Again, you may not even want to implement a search function. You may just say, hey, I'm gonna treat the index as my search function. Basically, I know if I go in here and throw an item at this index function, if it returns anything other than -1, I know that value is on the list. So it's essentially already doing the same thing as the search. But I wanted to show you those two different kind of implementations of those common operations you'll see on the linked list class.